Hello everyone again and welcome to the DMSI YouTube channel, and indeed it's truly a pleasure to actually have you all in this particular space. And in this particular video we're going to explore the relationship between the quantum numbers and specifically applying it to a question that involves principal quantum number of a shell is equal to a number, and what are the types of orbitals that will be present. And so looking at this particular question, you're wondering, where should I start from? Start by looking at the question itself. The question actually gives you some really deep insight into what to actually expect and what to actually move forward with. So in here, we know that in this case, we are dealing with a couple of things here. We're dealing with principal quantum number. We're dealing with a number which is in this case is equal to 3. And the question is asking, what are the types of orbitals? So looking at these, the solution specifically, we know that we need to actually establish first, what are the quantum numbers that are actually out there? What are the significance of the quantum numbers and how is this applicable to this question? So looking at this here, we know that, hey, we have 4 quantum numbers, and these 4 quantum numbers, they come in different states and explanations on how that leads to our final quantum number, which tells us that electrons, they don't have the same quantum number. So let's look at this combination of quantum numbers. We have the quantum number which is represented as n, and n is actually called the principal quantum number. And so the next one here is actually called the L, and L is represented as the angular momentum quantum number. And then our next one here is actually called M subscript L, which is called the magnetic quantum number. And finally here is actually called the MS, which is represented as the spin quantum number. So let's look at all these 4 quantum numbers in detail and looking at what each of them represents and how this might be important in solving our problem. So take note here, for our problem, we need to know what the number of orbitals, the types of orbitals that are present in that specific principal quantum number. So looking at this here, it means that we already know what we are going to be starting off with. We know that we're going to be looking at n, which is related to our specific question here, which is the principal quantum number, and we need to relate it to another, any of the other 3 that we don't know yet. So what is the principal quantum number? The principal quantum number in this case tells us the energy levels, and the energy levels of that specific system is actually a base for which electrons actually needs to be in. And so in this part here, we know that the energy levels was actually established by Bohr in a way that he was able to actually look at a hydrogen atom, and then he observed that, hey, electrons, they move from one point to another depending on the energy that it actually gains, either in the form of photons with a specific wavelength, and that we're going to talk about on our next video with a specific example, so watch out for that. But in here now, looking at the Bohr hydrogen atom, they realize that, hey, there are specific energies that are discrete, and these discrete levels, they start at specific levels where we have n is actually positive integers. And what are integers? Integers are known to be real numbers that are actually whole numbers, that are positives. So we're starting not from 0, but in this case you're starting from 1 to whatever number that you are going to be focusing on. So in this case here, when n is equal to 1, we know that that is what? The ground state, which is the energy level. And then n equals 2 is actually the upper level, looking at the atom right here. And then n equals 3 is actually higher than that. So in this case here, as you move up in integers, we increase in the specific atomic radius or atomic radii, depending on how many, either you have more than one atoms or less, so atomic radius. So this is one thing to keep in mind in here. And so once you have this taken care of, we need to then look at, okay, since we know that our question actually is focusing on energy level 3, we then need to look for how this is going to be important in our next part, which is any one of these 3. And so let's move to the next quantum number. And the next quantum number here we're going to be looking at is angular momentum. And so angular momentum here, quantum number, actually is represented as our specific alphabet, which is L, and this actually signifies the shape of the orbitals and those orbitals or sublevels that are present inside the energy level, which is n. So therefore, in this case here, we can establish the types of orbitals based on this particular formula, L equals n minus 1, where n is the specific energy level in question. So therefore, in this case here, where n is equal to 1, what is L? L in this case is equal to 0, which means that the shape of that particular orbital is equal to S, which is spherical. And the next one here is when you get to the next energy level, we have another orbital introduced to the S orbital in the second energy level. Therefore, in this case, to prove that, we put n in that equation and we find our L to be equal to 1. And so L equals to 1 actually represents p orbitals. Well, I'll say p orbital. So in this case here, when you get to energy level 2, you not only have s orbital in energy level 2, but also you have p orbitals. But there's no other orbital. We only have 2 types of orbitals in when n is equal to 2. So, but now the next question here is, how about n equals 3? We put n equals 3 into our equation, and what we realize is that L is equal to 2. Therefore, we not only have s orbital in energy level 3, but also we have p orbital, and we have L equals 2, which represents our d orbital. And so this actually is a way to determine the types of orbitals that are present in a specific energy level. So in this particular case, in conclusion, we can actually conclude, or we can actually state that, hey, for R, and this is a bad color to choose because no one can see that. I mean, I love yellow, of course, but not in this context here of writing stuff down. So let's get this erased and then use a different color. And so in this particular case, for our ground state, we only have, in this case, one type of orbital, which is S. And for our second energy level equals 2, we have 2 types of orbitals where we have 0 and 1, which in this case is spherical, and we have p orbital. And then finally, our n equals 3. We have 3 types of orbitals, which in this case is 0, 1, and 2, where 1 is the s orbital, which is spherical. We have the next one, which is the p orbital, which has lobes in its form or shape. And then finally, we have our d orbitals, which is, in this case, you have different 4 segments with a weird one that looks like Saturn, which is kind of impressive, but really cool looking at it in that particular model. So in conclusion, what is the answer here? Our answer here is that for n equals 3, there are 3 different orbitals that are present in that particular energy level. And that is how it's done when it comes to other types of orbitals. When n equals to 4, what will be L? L will be equal to 3. In this case, 3 represents our f orbital. And that means that our n equals 4 has 4 different types of orbitals, and this actually will probably on our next video lead to what is the magnetic quantum number, which tells us the orientation of the orbitals in space. We know that s orbital doesn't have any orientation because it's just spherical. However, our p orbital will have 3 different orientations, which will be important for our electron distribution related to our spin quantum number. And so for our next one, which is our d orbital, it will have 5 different orientations, and those 5 different orientations, because as you get bigger in size, you're going to have more space or diffuse spaces for electrons to be positioned. And in terms of thinking about electrons, you will go to think about the spin, where one will be spin up and spin down, and this actually has to obey the Pauli exclusion principle, which introduces us to fermions and so many interesting concepts in not only chemistry but physics. So that's about it for this particular video. I hope you're able to understand how to actually determine the principal quantum number, well, technically how to determine the types of orbitals using the principal quantum number, in this case given to be equal to 3. So that's about it for this particular video. I hope you actually found this informative. Hit a comment down below, let me hear your thoughts. That way I can talk to you soon, and please don't forget to subscribe, because hey, subscribing is free. And see you on the next one. Stay smart as always, and believe in yourselves.